So, there could be also more complex cases, let us say this expression that I have written. Okay. So, the problem is that you can easy to see how to apply this uniting theorem. I have just showed you how to apply this uniting theorem to make further simplifications. For example, you can let us say look at maybe you can take some a bar common, right, or maybe BC common. So, if you see this particular term and this particular term, you can group this BC together, right, and then it becomes A plus A bar is going to be 1. So, BC is going to be a separate term that remains. Okay. And after that you can do further simplifications, right. But what is problem is that whether you have applied the uniting theorem at the right places. Okay. Because just being greedy, I could see this value BC sitting here and this BC sitting here, this term sitting here, and that kind of intrigued me to start combining them, right. So, it might not be the best choice, because you may do one step of simplification and after that you might be stuck. This becomes, for example, that BC could be taken common, A plus A bar plus the rest of the expression is A B bar C plus A B C bar, which is again BC plus A B bar C plus A B C bar. What exactly you are going to do next, right. So, depending on the problem or depending on the case, it may be simplified, right, but I do not know whether I would go in this direction, which terms to club together and all, right. So, it is hard to know that you have applied the theorem in the right place, unifying theorem in the right places or not. The next is especially in a function of many more variables. So, we might have 4 or 5 and so on. So, in those cases it becomes a little bit tricky. So, the question is there an easier way to potentially simplify these kind of expressions, and where should you apply the unifying theorem or the uniting theorem. Okay. So, the answer is we need some kind of an intrinsically understandable and a geometric representation for any Boolean function f. Okay. Because whenever you write this long algebraic expression, you go into this, by default you go into this inspection mode, right. You keep on searching for parts of the expression that could be joined together to or merged together to apply the unifying theorem or uniting theorem, right. But often that is, as I told you, that you do not know how exactly should you go about, whom should you group first, whom should you group after that, and so on. We need a better technique, and the answer is that we need an intrinsically geometric representation of the Boolean variable, Boolean function. Okay. And we can draw and see them, that who are really neighbors, right, or for an onset whether it goes from 0 to 1, that we can visualize. Okay. So, that is done by using this map technique called the Karnaugh map, which is named after its founder, Karnaugh map or K-map method. Okay. So, this is a technique we redraw the truth table in a very specific form. Okay. So, all of you are kind of aware that the truth table, the way we were writing it is, you have this columns where the initial few columns were the list of inputs, followed by the few columns that is the list of outputs, and we have all possible different rows of the inputs, right, and leading to that output. So, if you had n input variables, you would have ideally 2 to the power n different rows in the truth table. So, K-map, what it does is an alternate method of representing the truth table that helps visualize adjacencies. Adjacency means A and A bar are there, B and B bar are there together, right. So, this is called an adjacency up to 6 dimensions. So, I will try to give you a very concrete idea till 4 dimensions. 5th and 6th will be a little bit more involved. So, I am not going to go into the 5th, how to do it for 5th or 6th dimensions, but up to 4 dimensions it will be more than enough to get the idea. Okay. So, what we need is called adjacency, and adjacency means they should be neighbors in this particular diagram that I have shown. So, note this term called physical adjacency is equivalent to logical adjacency. Okay. So, if you see B, right, so 0 and 1 they are adjacent to each other. So, this is 0 0 is A is equal to 0, B is equal to 0, 0 1 is here, A is equal to 0, B is equal to 1. So, these columns are representing the values of B, these rows are representing the values of A, right. In that way you can find out any other things, right. A is equal to 1 and B is equal to 1 is 1 1. Similarly, if you look at the 3 variable K map, we have this value similarly listed up. One interesting point that you should look at here is that if you had 0 0, so these are the values of B and C, 0 0, after that I have 0 1, ideally you should have 1 0, right, because 0 0 logically is like 0, 0 1 is the next one. In a truth table after 0 1 you will have 1 0, okay. But however, we are using 1 1 next and then only 1 0. So, you might think this is strange, but there is a reason why we are doing it. The reason being that we wanted the variables, or we want the variables to changing one at a time. If both variables change simultaneously, it will be difficult to track that how do you club them, right. So, 0 1 this actually means B bar and C, okay, but 1 1 means B C, okay, and 1 0 means B C bar. So, if you actually had 0 1 adjacent to 1 0, B bar would change to B and C bar would change to C would change to C bar. So, both the bits actually flipped, right. So, it will be not possible to there cannot be considered as them adjacent, because the rule of this uniting theorem is that you have to choose the particular variable that changes its value, okay. Here if you see B bar C and BC, if you concentrate on just the B variable, B and B bar they change, so they could be potentially grouped together, whereas C is just going to lie just like that, okay. So, please keep this in your mind that whenever we are kind of tabulating the K map, you have to write the variables in a systematic way such that only one bit flips, okay. So, 0 here also you see 0 0 only one bit flips and it becomes 0 1, only this last bit flipped. From 0 1 I cannot go to 1 0, I can only go to 1 1, or I can also go to 0 0. If you flip this one it will go to 0 0, if you flip this one it will go this way, okay. From here if you flip again, if you flip this one it will go this way, but if you flip the last one again it will become 0 1, okay. So, all this sequence is very important, right. In this sequence only one bit flips occur, that means that only one variable changes its value from complement to non-complement or non-complement to complement, either one of them, okay. So, this numbering scheme has a special name, right, it is called gray code. It is a sequence in which a single bit change in the code word changes its value, right. So, you have a sequence of these codes, let us say the 3-digit number, 3-bit number, or a 4-bit number, or a 5-bit number, and you have a sequence of these 5-bit numbers. So, as you have the sequence of these 5-bit numbers, in between two successive numbers you should have a difference of only one bit, only one bit should be should have been flipped, the rest of the bits should be exactly the same, okay. So, they have many different applications in various things like error corrections and so on, or designing codes, but we will not go into those details. Currently we will just focus on the naming convention. This is a gray code is the name of the convention, and the way to do it is that you should remember that only one bit is going to flip. And why we are doing it, that is also very clear. We are doing it particularly because we want to apply the uniting theorem, and uniting theorem can only be applied in a situation where everything being constant, only one variable changes its value from 0 to 1 or 1 to 0, right. It is simulating that bracket that we are using. Let us say it is AB bar plus it need not be AB bar, it could be X, Y, Z, AB bar plus X, Y, Z, AB, right? Doesn't matter. So, all you have to do is X, Y, Z, A, B bar plus B. So, we have filtered out everything else other than B, because this B and B bar should be adjacent to each other, and you can see that it changed its value and you can club them accordingly. And there are one more thing that you should remember is that it's not only you have to group the terms adjacent to each other inside the map, but at the same time you also have to wrap the map in some way. So, what is the wrapping thing means? What you have to basically think of this in terms of a paper strip, right, and as if joining this end with the other end, right, which is shown in this figure on the right hand side. So, you can see 1 0, if you do if you flip this particular last bit, right, it will come here, right. If you are flipping 0, it will become 1 1 and come here, but if you flip this particular bit, this is again going to go back to 0 0. Okay. So, technically this is C is equal to 0, here also C is equal to 0, but B changes its value from 1 to 0, which means that you can club this last term to the first term and still apply the uniting theorem, because B then vanishes, right. Here B is equal to 1, here B is equal to 0. Okay. So, not only the adjacent terms, but adjacent terms also in a wrapped sense. I will give you some more examples that will make the idea very clear. Similarly, you can also do it like this, right, which is shown in the figure here. So, if you look at this term, top and bottom, 0 and 1, right, they are adjacent to each other, right. It will become more clear in larger K-maps, but the way we group terms together is not only just adjacent or logical or this physical neighbors. One is physical adjacency, the next one is this adjacency in the term of the wraparound sense. Okay. So, if you take the hypothetical this transform truth table, or typically this is called the K-map, and then wrap it around both horizontally and vertically, whatever terms are going to be adjacent to each other, that could also be grouped together to apply the uniting theorem. Okay. So, wrap around from the first to the last column and wrap around from the top row to the bottom row. So, K-map cover 4 input variables, there are A, B and C, D, and this is the given K-map, let us say. Okay. So, wherever you have one, this means that that particular min term is present, as simple as that, right. So, given a truth table, you want to write down in terms of the values of A, B, C, D. So, for example, let us concentrate on this term, right. So, this term is nothing but an intersection of this 0 1. So, A is equal to 0, B is equal to 1 and this term, right. So, E is equal to 1, D is equal to 1. So, the corresponding min term will become what? A bar, B, C, D. Okay. Similarly, if you choose, let us say this one, this is A B bar, right, whereas this one is C D bar, right. So, this one becomes effectively A B bar, C D bar. So, this is the corresponding min term. So, given the truth table, you should first draw the columns and the rows of the different variables in terms of the gray code numbering system, and then fill in the individual values from the truth table to this map. Okay. So, in this case, this is going to have this many min terms. So, how many min terms are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, there are 11 min terms, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, there are 11 min terms and we have written it as a sum product expression. You can always write it as a truth table. Here we have written it as a SOP expression and also drew the corresponding K-map. Okay. So, now what we should do, we will try to simplify this expression, right. So, F is equal to what? we have to simplify this. So, this could be the simplified expression, you can try it out, but the way we do it is this, right. We want to group terms together, right, such that they could be simplified. So, as I told you, if there are two terms next to each other in the onset, they could be grouped. You remember earlier that if it is onset and there are certain terms that are next to each other, we can always club them and apply the uniting theorem. Here it is a same thing that we are doing. You have to consciously think about it. We should group all the terms that are adjacent to each other such that and this is as large as possible. So, if you see, this is all ones, right. So, the all ones may be, instead of doing this simplification and this simplification separately and then doing this simplification separately, we chose all the ones that are together. Okay. So, in doing so, what happens is, if you see along this direction, right, 1 and 1 for A remained, whereas this thing it vanished because B and B bar, it was 1 and 0 that got cancelled out. If you look at this, right, it has all the different min terms. It has C bar and as well as it has C bar D bar, and this is your C bar D, right. So, this is going to cancel out D. Okay. Similarly, you had C here and this is D plus D bar, right. So, this also gets cancelled out, it becomes C plus C bar, and that also does not matter, C plus C bar becomes 1. So, ultimately you are left with only A. Okay. And you can do, so that was the first one. So, that is how you got A. The next one is you can do this wraparound simplification, right, because this one, if you wrap the paper, touches with this one, and if you do a vertical wrap up, this one touches with the last one, right, that, and those ones have not been grouped together earlier. Okay. So, you can have a large one large combination of these corner ones, and what will be the output of these corner ones? Let us try to ask this question one more time and try to see whether we are understanding it or not. So, the corner ones, so let us concentrate on this one and this one, right. If you see what is the common here, the common column name, right, this is C D bar, right, C is equal to 1 and D is equal to 0. So, C D bar, whereas these values, this has AB is equal to 0 0 and here A is equal to 1, B is equal to 0. So, here B did not change, right, B was always 0 and A changed from 0 to 1 in this wraparound, right. So, this will be B bar, right, the contribution from these rows for these twos will be B bar, and this is C and D bar. So, B, C, D bar, but our we have group is little bit more than that. So, from this direction we were able to eliminate A, because A was, this is A and this is A bar. So, we are able to eliminate that, but B bar remained. Okay. So, B bar remained, and let us look at the horizontal row. We had C and D bar, as well as in the first one we had C bar D bar. Okay. So, D bar is the only thing that does not change. It was 0 here, it was 0 here as well as 0 in the first entry. But whereas C was changing its sign from C to C bar. If you look at the first bit 1 and then 0, it is changing, right. So, only thing that is going to be remaining is the D bar from the top horizontal line and B bar from the vertical line. So, B bar D bar, as you see, is the expression for simplifying the corner ones. Next is these two, right, they are adjacent to each other and this particular top one has not been grouped yet. So, in this case again this vanishes because 0 and 1 A and A bar, they vanish. Only thing remaining is B in the vertical line. In the vertical line there is only B because this is 1. B remains, and here look at view. And in the vertical line, this is your CD. So, C bar, this is C bar D, okay, because C is equal to 0 here and D is equal to 1, and you can see it here. So, B C bar D. Okay. So, the strategy for circling these rectangles on K map is you should circle them as big as possible, okay, and do not forget the wraparounds. So, you can very easily see that there are all these ones are here, you can do this enormous circle, you can do this circle, but often you might forget to do this, right. Even if you did not have ones on this corner, still it is okay to group this and this, okay. But you need to remember that you have to wrap around the corners for the most simplified expression, okay. So, this is the technique by which you, given a truth table, you can convert it into a simplified expression using the K map, right. So, this is your simplified expression. Now, think about it that if you had the SOP and then you were trying to do this manually just by using grouping, it would have been a nightmare, right. It would be a enormous expression and you would be figuring out whom to group with whom and doing some simplifications just like that, right. So, this may make your life difficult, okay. This is a easy way to do, and it is mostly mechanical. As long as you are paying attention to the different ones and you do the circles properly, that would not be a problem. Okay. So, if you look at the logical gates schematic of this particular expression, this will become is very simple now, right. Compared to that, compare that with the 11 or 12, I think 11 min terms we had, right. So, 11 min terms, 4 variables, right. So, there are 4 input AND gates and an OR gate that has 11 inputs, right, that is enormous, whereas we can do it very, very simply, right, just with 2 AND gates and 1 OR gate, okay. So, this is how you can be rest assured that the logical schematic is very, very simple. So, the simple guidelines are as follows. These are the very simple things to do. Circle all the rectangular blocks of ones in the map using the fewest possible number of circles, okay. So, you need to make sure that all the blocks of 1 in the map are covered, okay, and they have to be as large as possible. So, each circle should be as large as possible. That is why we said that using the fewest possible number of circles. You have to group them. First, you have to be very greedy and group the largest circle, right, then the next largest circle and so on, right. And whenever you are circling something, you can read off the implicants that were circled. So, implicants means the product of terms, if you recall, not the min term has all the different variables that are present, but implicants is just in the product form, okay, ANDed together. So, what for a given circle, a particular circle represents what implicant, okay. So, if we go back to this example, this huge rectangle we had was A, right, whereas this small circle, right, the corresponding implicant was B C bar D, okay. So, this is the rule that you should mark the circles which are increasingly larger in size, or starting from the largest circle you should go down, and more formally a Boolean equation is minimized when it is written as a sum of the fewest number of prime implicants. This is a more formal definition, but that is what exactly you are doing. So, you are minimizing the equation as it is written as the sum of the fewest number of prime implicants, because you cannot group them anymore, right. So, prime implicants are these, right, which do not it cannot be grouped together anymore, right. So, A is completely different and B bar D bar, right, and then B C bar. So, these are the prime implicants, and the number of prime implicants here in this sum is minimum. Then you can assume that the Boolean expression has been minimized. Each circle on the K map represents an implicant. That is what I told you already. The largest possible circles are the prime implicants. Okay, so you have to keep this in your mind, and you can use this for a few example truth tables that we will be giving you as assignments, or we will solve some problems in class, so that you can get an idea of how to actually use K-maps for in practice, right. So, I showed you one example, but we need to go to several examples so that the method is clear to you. Okay.